Hello everyone, this is my completed SAR ADC. First, we can see the prototype of the SAR ADC going from 0 volts to 5 volts. While watching this, I would like to give a big thank you to Mitsuru Yamada for coming up with the idea behind how to create the SAR ADC and providing a very informative hackaday on how it works. Here we can see an oscilloscope view of the working SAR ADC. Here I've chosen a random voltage of 1.31, and as we can see, the successive approximation register first checks the most significant bit of 2.5, sees that it is less, then goes down to 1.25, sees that it is greater, and continues this process until the 7-bit value is created. For an extension to the project, I swapped out the potentiometer's input for a Wine bridge oscillator input. Sadly, because of how fast the waveform is going, the bar graph will always just show all 7 bits high, so the oscilloscope reading shows the really cool successive approximation that goes on. As seen, because this is a 0 volt to 5 volt successive approximation register, the troughs do not read anything below 0. Now let's get into how the successive approximation register works. For starters, we will go through what happens at the end of the last successive approximation cycle. At the end of the last one, Q6 sent a clock pulse to the 7 flag, and right after that, Q7 was sent a clock pulse as well. This did two crucial things. One, it set the 7 flag high, which we'll talk about in a second, and secondly, it set this clock to be cleared and set all these flip-flops to have a predefined of 1, making all the outputs a 1. This is very crucial to know. Next, what happens is because of the 7 flag going high, we know that now whatever value is at the potentiometer is now being held at the non-inverting pin of the comparator. In this case, we're choosing the value 1.31 volts because we looked at it with the oscilloscope. Now, after this, because this was cleared, it's going to go back to the very first output, which is Q0. And the one thing to note is that right after these predefines were high, because this is high and this predefine was set to a 1 value, it means that this section of the R2R was set with a value of 1. What that means is that now there's a comparison between the most significant bit of the R2R ladder and the analog input of 1.31 volts. And because we know that 2.5 is greater than 1.31, the output is going to be a 0, which sends that back into the data pin right as the 1 clock pulse is sent through. This 1 clock pulse sends the data pin low and means that this AND gate will no longer be high and will always stay low, meaning that this section of the R2R ladder becomes a 0 for the rest of the successive approximation cycle. Next, we go to the second AND gate. At this point, what you can realize is that the 1 clock pulse is set to a high, meaning that now this section is a 1 and a 1, meaning that because this is a 0, because of the previous comparison, now all it is checking is that it is comparing 1.25 and 1.31. And because we know 1.31 is greater, it sends a 1 back through this section, and right as the second clock pulse is coming through, it means that this is a 1 and this is a 1, unlike this part where this was a 0 and this was a 1, and this means that this 1.25 will stay, giving us 1 bit of the digital values of the analog input. This continues for the rest of the cycles, and the output is outputted through the second one as the Q7 flag sends this value high, giving us the 7-bit analog value in digital form.